Welcome to my presentation, Ecosystem Flux Simulation with a Scope model. The work was done under the supervision of Christian van der Tol and Mirko Miljavaka, and my name is Egor. A little bit more about my background. It is in plant physiology and biochemistry and also bioinformatics. Currently, I'm finalizing my PhD in the University of Twente, Faculty of Geoinformation Science and Earth Observation. My PhD was funded by Maria Curie project, the Trusty project, whose background you can see on each website. The project has already finished, so I encourage you to follow the link and see what our team of 12 PhDs has made in remote sensing. In those 6 steps, I'm going to explain you what a biologist has done in a remote sensing world so far. And let me start with the motivation. As you know, the Earth is a closed system. It means that energy exchanges, but the matter circulates, so it stays. And you know this cycle of carbon, of nitrogen, of water. But the ecosystem, in contrast to Earth, is an open system. So it exchanges matter. And those matter exchanges are what we call flux. There are 2 types of flux that I will cover in this presentation. First is carbon flux in the way of gross primary productivity. That is the rate of photosynthesis, so to speak. And it's measured in grams of carbon per square meter per day, for example. Water flux is a tricky flux because you can measure it as matter. Then we talk about evapotranspiration, so evaporation plus transpiration, and we measure it in millimeters of water per day. Or it can be measured in energy terms. Then we call it latent heat, the remainder of net radiation minus sensible heat minus ground heat flux. And then it's measured in watts per square meter. I will use both terms, ET, LE, interchangeably, but they essentially mean the same thing, and they're connected through the water, latent heat of water evaporation constant. And the question is, why to monitor flux at all? Of course, from social perspective, it has a food security reasons, because it's important, for example, to water plant adequately. So the plant evapotranspiration is a crucial factor to both give enough water and to save fresh water. In the view of climate change, I can mention here the policy makers, such as European Union Climate Adaptation Strategy policy. They are looking for such tools for ecosystem related decisions. But for us, although we, of course, are part of social, the scientific interest, so the curiosity is the main driver, because to be honest, the best way to measure, to monitor the flux is to measure the flux. But we are not happy with that, because if we measure something we cannot model, so we measure something we don't understand, we cannot predict. So scientific question is actually how to properly simulate flux. And this can be done well, a little different for GPP and ET. For GPP, typical modeling approach is to use a single leaf photosynthesis and then upscale it somehow to the whole canopy and ecosystem with big leaf model, 2-leaf model, multi-layer models. For ET, there are 2 sources. It's a soil evaporation, presented here, and vegetation transpiration, presented here. Both modeling approaches are based on gradient diffusion theory, where vapor pressure deficits between the bottom and the top and aerodynamic conductances in between are the moving factor, the moving force of water transport. So we're talking about 2 source models, so both soil and vegetation component contribute, so it's evapotranspiration, or there can be, again, multi-layer models. Notice that up to now, I haven't said anything about scope model, because those concepts, they are common for many land surface models, if not all. So now we're coming to scope. A Soil-Canopy-Observation for the chemistry and energy balance model was presented by Christian van der Tol 2 seminars ago, so you might be familiar with that. But this is the conceptual scheme that we have in the paper that is under review, but it's already available at the bottom of the slide. Essentially, what you may know well is this procell log that simulates radiative transfer in optical domain, in fluorescence domain, and also external cycle dynamics for PRI index calculation, for example. But this presentation will tell you about the top part of the scope, the energy balance, live biochemistry and aerodynamic introduced above. So we explored this link between optical and energy balance domain. We analyzed these flux outputs, and we will touch a bit the loop of thermal radiation. Of course, we are not the same. We're not the first who studied flux with scope, and there has been a bunch of works of direct application of model for rapeseed, for grassland, cropland, shrubs, and also it was used out of the box on that ecosystems. Also, optimization approach has been suggested by Dufour and by Dutta. Indirect applications, but I mean that not energy balance was used, but the link between energy balance and solar-induced fluorescence was discussed in the works of colleagues and combined in a Betty scope model. Also recently, transpiration and solar-induced fluorescence link has been developed. So how we contribute here is we want to use the model directly, but to find out which parameterization works best for, let's say, all ecosystems. So not only grassland or not only cropland specific parameterization, but in general, large scale parameterization of scope. And here we come to the objective. As I named the question, the objective is to learn how to parameterize scope model for different ecosystems. And we have 3 options. Vegetation functioning is the first one, as is the main focus of this study. So the Rubisco carboxylation capacity parameter that defines the rate of the photosynthesis. What is better, the literature value, the default value, or something else? Then vegetation structure parameter is what explores the link between optical and energy balance domains. We'll use leaf array index retrieved from Sentinel-3 top of atmosphere data. And environmental factors are from ERA 5 data. In somewhat visual way, the same as has been said before. So we run scope model, parameterizing it with vegetation functioning parameters from literature, leaf array index from Sentinel-3, meteorological data from ERA land, and the resulting flux we compare against eddy covariance measurements. Let's go one by one on how we got those parameters. First one is vegetation functioning. And here you can see in the table the values that we used, maximum carboxylation capacity parameter, and the slope of photosynthesis model, and the Bolberry slope of stomata conductance model across 6 plant functional types: cropland, grassland, savannas, evergreen needle-leaf forest, mixed forest, deciduous broadleaf forest. Default value is 60 and 8, and those values you can find in the paper of Grunendijk et al. In 2011. You can see how those parameters influence cross-primary productivity flux on top and evapotranspiration flux in the bottom. Basically, the higher, but the response is non-linear. And for example, here it saturates almost at the value of 6. Then we added seasonality because the research says that we have to. consider that Vcmax value changes and it's different in spring, summer, and autumn. Therefore, we used leaf area index and the scaling suggested in the paper of Young-Roel. But to apply leaf area index scaling, we have to know what leaf area index is. And therefore, we use Sentinel-3. This is a European MODIS. So release time is 1 day, and we have higher probability of having more cloud-free images. It has simultaneous observations in thermal and optical domain, most insensitive bands, and it has bright future to be coupled with fluorescence explorer mission. But there are limitations. So each point, for example, this in central Spain, is viewed indeed daily, but from different angles each day and from different orbits. That enlarges the footprint from the expected 300 meters to almost 1 kilometer. This issue was described in the paper you can find here. Another limitation is the data availability. Although April 2016 seems not so far, very far ago, for flux monitoring and for time series analysis, this is very short periods. And since April 2016, it's available in top of atmosphere, so not atmospherically corrected images, level 1. And only in October 2018, they start producing top of canopy reflectors. Therefore, we had to understand how to retrieve from top of atmosphere data. And for that purpose, first of all, we conducted sensitivity analysis. Here you can see atmospheric parameters, canopy parameters, leaf parameters, and soil parameters, and how they influence each wavelengths. The details are presented in that paper. So, having understood the effect of atmosphere, we model this in a SPART model. So we add on top of Procyle the modified atmospheric model. And then we did inversion. So we put top of atmosphere radiance in, and we got leaf area index out. The details of the algorithm is described in the paper. So overall, now you know more. Scope was parameterized with Vcmax values per plant functional type, either constant or seasonally varying. Leaf area index was retrieved from top of atmosphere data with SPART model. And radiation, temperature, humidity, and surface pressure were taken from ERA-Land 5 dataset. Validation was conducted against 23 ICOS sites from drought 2018. And as I said, it's too recent, so we had only 2.5 years for validation. By the way, both models, the updated version of Scope and the SPART are available in GitHub. Final slide of methods and the validation. Those 23 sites were located in Europe in different climatic zones: boreal, continental, temperate, and subtropical Mediterranean. And there were 2 cropland, 3 grassland, 3 savannas, 9 evergreen interleaf forests, 2 mixed forests, and 4 deciduous broadleaf forests. If you have ever worked with flux nets, you know that they provide a lot of different GPP values. So the one that we used is the GPP with nighttime partitioning of net ecosystem with variable U-star threshold and with 50 quantile distribution. Then latent heat flux, there were also several options, and we have chosen the corrected latent heat flux, corrected for energy balance closure, because Scope always closes energy balance, but measurements not often. I would say often not. Therefore, there is correction. The correction was done by FluxNet algorithms, by FluxNet people themselves. The results. Let me have a sip of water. The most exciting part. Here you can see results for cropland, grassland, savannas, evergreen, daily forest, mixed forest, deciduous broadleaf forest. This is GPP daily flux, and this is mean seasonal cycle. So this mean of those 2.5 years. The blue is the measured, the orange, the default parameterization, the green is the plant functional type dependent parameterization. Where you see the green smiley face, cropland, grassland, mixed forest, is the cases, the ecosystems when plant functional type dependent parameterization outperformed the default parameterization. And savannas, evergreen daily forest, deciduous broadleaf forest are those cases when default parameterization outperforms. We go to latent heat flux. You see that the difference was not that big. Probably, if you remember still, the sensitivity graphs I showed you, because of the saturation of the Bohr-Berry response, so that not much difference in ecosystems. And what immediately pops up is that everywhere is all okay, but in drought ecosystems, during drought period in savannas, the simulation are not reliable. It's a good idea to analyze not only daily flux, but also annual sums. So what you can see here is the cross-site variability, measured flux on x-axis, modeled flux on y-axis. Each point here represents the average of 2.5 years for single site. So 1 point, 1 site. And different colors are for different plant functional types. You can see that the simulation of GPP, I might say, outstanding. You might argue in the discussion, but it is really good. And already it's good in its default parameterization. And plant functional type constant value by itself does not performs worse. You see the bias became negative, and the correlation and the root mean square error was higher. However, if we add seasonality to Vcmax values, then we see that the performance is even better. So I mean, root mean square error is the same, but the bias is reduced. So this curve has constant positive bias, and this one is good. Evapotranspiration also was simulated well, but those outliers in subtropical ecosystems, they of course make the matter worse. So to conclude, I can say that SCOPE reliably simulates both GPP and ET flux at both daily and annual scales. However, for drought-subjected ecosystems, ET flux was not reliable, but GPP was okay. If the target is to monitor water flux in those ecosystems, I might suggest those papers of that show how to adjust SCOPE to work in that ecosystems. We were using out of the box, so no tuning was done. Then, a little surprising conclusion, but the default parameterization of Vcmax equals to 60 micromole per square meter per second already gives good results for most of studied ecosystems. But indeed, seasonally varying plant functional type dependent parameterization reduce the bias in GPP further. Before acknowledging your attention, I would like to have one thought, like a food for thought, the limitations. What I have been talking about is this part, for example, of carbon cycle. It's photosynthesis. And furthermore, it's gross photosynthesis. So no respiration was included here. But this is definitely, if we want to understand the whole carbon cycle, this is definitely only one part of it. Furthermore, my talk was focused on terrestrial ecosystems, but we know that 25% of CO2 exchange takes place in oceans. So what I want to say with this slide, that we have to collaborate and synergistically collaborate to understand that Earth breathing Earth system. Thank you for your attention.